Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Sunny He, who will tell us about composable quantum fault tolerance. So Sunny is a graduate student at MIT, advised by Peter Shor and Anand Natarajan. He is broadly interested in quantum information science, focusing on quantum error correction, and he research designs fault-tolerant computational architectures for quantum LDPC codes, specifically extractor architectures with theoretical guarantees and near-term applications. So, Sunny, the floor is yours.
Ah, yeah.
Mhm,
Thank you, Gello, for the
mhm,
nice
mhm,
introduction, and thanks for having me in this group. I really appreciate it.
mhm, mhm,
So today I want to tell you all a little bit about this recent work called Composable Quantum Fault Tolerance. This is joint work with Quinn Nguyen and Christopher Pattison. Um, so the title says quantum fault tolerance, but I want to start this talk with a little bit of his story. So we were at this, the story starts in Benasque, which is a small mountain town in Spain. Where was I? Yeah, we were at this workshop. It's called FTQT, Fault Tolerant Quantum Technology. We were there in August of 2024, and it's mountains all around. So all we do was we give talks, and we were hiking, a lot of us. Now, this is the group photo we took, and there are two person I want to highlight here. One of them is Chris Pattison, who is one of the co-authors on this paper. And the other one is Ken Brown, who is a professor at Duke University that does error correction. I highlight Ken because we were sitting in this breakout sessions where we're assigned into small groups and we need to write down questions we like to understand better for this workshop. And Ken, who's in our group, asked the first question of the workshop, which is, what is fault tolerance? And that's his exact words. I didn't shorten it, didn't paraphrase it. It's just those four words. And if you see the title of this workshop, that's kind of the first two words of this program. So it's kind of saying that for experts, for quantum error correction experts such as ourselves, there seems to be a lot of different ways and a lot of different notions of fault tolerance that we are considering and that we're interpreting. And there seems to be a lot of discussions around this specific terminology. So this is the question I want to start with today, which is what is fault tolerance? And let me maybe give a little background because I was told that the audience may not from a QEC background. So let me give a little bit of motivation. So the theory of fault tolerance is really motivated by the fact that we want to run large quantum algorithms such as factoring or quantum chemistry. And our current physical devices are very noisy. They're not able to support this kind of large scale applications. So usually we measure in terms of circuit volume. So the width of the circuit times the depth of the circuit, we denote it V. And for fault tolerant execution, we want the gate error rate of every gate to be roughly 1 over V. That guarantees like a constant success probability. And for factoring, that number is around 10 to the 15. And our physical error rate today is around 10 to the minus 3. So the idea here is that this is why we need fault tolerance, which is we want to use this technique called quantum error correction to close this gap between the physical error and the logical error or the large scale error that we want to achieve. So how exactly is that done? That's this fault tolerant execution is done through this method called encoding. So we start with raw qubits, gates, and error rates. These are the unprotected physical error rates. And we encode them into error-corrected logical qubits and gates and error rates. So what that looks like pictorially is that we start with a circuit of certain widths and depths, and we encode it using like quantum error correction techniques, all the qubits and all the gates, into a bigger circuit, the encoded circuit. And this encoded circuit interact with a classical computer to help with its error correction. Now, we usually measure a few things here. We say, okay, what's the space overhead of this encoding? That's W prime over W. What's the time overhead of this encoding? That's D prime over D. And we often measure these overheads in terms of the physical circuit volume, specifically log of V. So this is the basics of quantum error correction, or the basic motivation of it. Now, coming back to the question, what is fault tolerance, and why the question, first of all? Um, the golden standard when we say, a circuit or a particular execution is fault tolerant, or a particular method of encoding is fault tolerant, is to say that there exists a constant noise threshold epsilon, such that if the physical error rate is below epsilon, then we can realize arbitrarily large computation. So this was one of the, for instance, the threshold theorem for quantum computing. This is one of its statements from Nielsen and Chong. It's a very time-tested result. It's one of the first indications that arbitrarily large quantum applications can be run in a physical world. Before this, there were really a lot of doubts whether that's at all possible. Now, if you read the statements, let's not go too much into the statements, but if you read the statements, this means that there's a family of encoding schemes, we usually call them FT schemes, such that they can achieve arbitrarily low encoding rate at growing cost. The space overhead and the time overhead will increase if you want to achieve a lower error rate. Great, so this is the kind of the gold standard of fault tolerance, and you might say, well, what's unclear about this, right? This seems like a reasonable theorem. There is a threshold. Below the threshold, we can just scale the computation or scale the encoding scheme and achieve like lower error rates. Well, there are a couple of issues here. First of all, what is the noise model, right? Are we working with a locally stochastic noise, independent Pauli noise, adversarial noise, or the more formidable coherent noise? If you have heard of this, you probably know that coherent noise is very hard to work with. If you have not heard of this, don't worry. Think of it as the biggest dragon of them all. The second problem that commonly shows up is, what are the computational assumptions, right? Do we have free and noiseless classical compute, or do we have other models of computation that we need to track of? And perhaps the most significant issue here is that such a statement, which we call a threshold theorem, it's really, really hard to prove rigorously. Okay? Most papers, so there are, of course, papers that prove this style of theorems, but most papers that shows up nowadays, they will propose different kind of error correction or fault tolerant techniques, but they do not prove like a full threshold theorem. Instead, they would justify fault tolerance in other ways. So let me illustrate what I mean, or give an example. Let's talk about LDPC codes, which some of you in this group may be very familiar with, but if you're not, don't worry about it. It's a pretty hot new type of error quantum codes that people have been spending a lot of effort on. And the specific example is, for instance, encoded computation gadgets on LDPC codes, on this type of new codes. There's a lot of recent papers proposing a lot of interesting ways to perform encoded computation. And this snippet is from a recent cover letter I wrote to submit a paper to a journal. And all of these citations are just very recent papers that did logical computation. And if you look at the citation list, most of them is in 24 or 25. It's very, very recent. And this is very incomplete. I think over the past few months, we have like maybe 5 to 10 more papers now. But there really is a lot of work. Now, with this amount of work, they all justify fault tolerance. They all propose fault tolerant techniques to manipulate these encoded information. But their fault tolerance also always have different definitions. They always work with different assumptions and noise models. And as a result, if you try to put them together, you can really combine them in a very rigorous fashion, or as rigorous as one would hope, because of the different assumptions. So in some sense, this is a lack of composability in the modern analysis of fault tolerance. And to really drive the point together, let me illustrate some of the other notions of fault tolerance besides that of a threshold theorem that we've been using. In fact, there's so many of them that I can fill a whole fault tolerance alignment chart. and there's still more notions that I have not included. So what is this alignment chart? How should you read this alignment chart? If you look at the horizontal axis, it says from lawful to chaotic, it's really to measure how rigorous the proof of certain notions are. And if you look at the vertical bar, it says good to evil, it really says how standard these notions are and how, or in contrast, how uncommon or hard to derive or hard to convince others of that these concepts really are. So one example, if we look at the lawful and good, is there a laser pointer I could use here? Laser pointer, great. So if we look at, for instance, this particular notion, it's called threshold under stochastic noise. People have proven quite a bunch of results like this. They're often very rigorous, and it's very easy to convince others that such a result is really fault tolerant, and if you run it in practice, it should work. Now, there's the other side of things. For instance, proving a threshold is really hard. Sometimes people just prove like large space-time distance. There's actually a lot of work on this as well. That's usually a little less rigorous than a full threshold proof, but it's still like a pretty good standard that people would agree with. But if we start moving to the evil camp, we start seeing a lot of things. For instance, sometimes we say, okay, we simulated on small instances, we perform numerical simulations, and we do not give like we give some, intuitive argument of whether this is fault tolerant. Well, that's still good evidence, but that brings the question of if we actually implement this physically, will that work? And of course, there's, for instance, threshold under coherent noise, which are all very rigorously proven, but they're very hard to prove. They're very uncommon. And, it's actually a very big open problem of how to prove constant threshold under coherent noise in different settings. So those are the few things I want to highlight. There's obviously the chaotic and evil, which is, you say that this looks fault tolerant, and you stare at the other party long enough so that they, they have to say yes. But of course, that's the chaotic and evil party of things. Now, looking at this alignment chart, this is really why, the question that Ken asked at the beginning, which is, what is fault tolerance? When we say fault tolerant, what do we really mean? I can move to the next slide. And the goal of this work and what I hope to present to you today is how to derive rigorous and composable fault-tolerant techniques and results. So this is, in some sense, a framework question, and that's exactly what we do. We propose a mathematical framework for proving threshold theorems that have a few very nice, I would say, properties. The first thing, and it's in its name, is that it enables composition of complex and drastically different gadgets. I'll showcase that throughout this talk of what I mean by this, but returning to the question earlier, if we have gadgets under drastically different assumptions, it's actually very non-trivial whether they will compose at all. And in this framework, we try to bring a lot of these less rigorously proven results closer to the rigorously proven side. And we also reestablish several well-known threshold results in the same language. So we try to unify the lawful camp a little more. Great. And perhaps conceptually, the way to think about this is that our formalism separates the probabilistic analysis of noise models from the combinatorial analysis of error propagation. And one of the things I'll say at the end is that we'll argue fault tolerance is really a combinatorial property of this discrete object we're calling a circuit. Okay? But that's towards the very end of the talk. Okay. But one of the hopes or one of the goals of this work is to build this framework such that future works can continue to prove new gadgets, but will be able to compose with the entire existing library and derive rigorous threshold theorems for novel fault-tolerant schemes. Or in other words, we want to make proving threshold theorems easier. I'll also showcase that towards the end of the talk. Great. Now, just to give a few examples of what we did with this framework. So we prove and reprove a few threshold theorems. There's a constant overhead fault tolerance scheme using LDPC codes. This is well known since Gottesman's, has been quite a few follow-up results that has used many similar ideas. We're able to re-derive the whole proof here. We give a first written proof. I put a question mark here because we set this at QE. We don't know whether this claim is true, but this paper were presented at QEC, the conference quantum error correction, and nobody really, attacked us for saying this. So I think this is correct, but we give the first kind of written proof of a threshold theorem using surface code and distillation. So this is like very, well accepted result that surface code has a threshold. We can do FTQC with it, and we can do magic state distillation. But this is really just giving a complete and self-contained written proof of it. And furthermore, we derive a threshold theorem for surface code FTQC under coherent noise. Okay, so this is actually a new result. The threshold we get is not constant, but I think it's still quite interesting that we're able to derive both results about locally stochastic noise and results about coherent noise in the same setting. And there are many possible future works, so especially if you're a student working in quantum error correction and is interested in potentially proving fault tolerance theorems, I'll showcase a bunch of problems that can be worked on towards the end. Great. So with all of that being said, let me get into the framework. I think I'm doing well on time, so I will keep this talk mostly not too technical. I'll hide most of the notation away. The paper is 80 pages long. We won't go over all the notations and all the mathematics, but I do want to give the high-level idea. Great. So I say that we unify a lot of the lawful camp. And the first thing I should say is, what is our model of a circuit and what is our model of a fault? Because there are many different models of circuits and faults. And if our model is not general enough, then we can't derive all the results we want to derive. So we consider a fairly general model of circuit and faults. So this is what a circuit looks like. The left and right, these are the input and output nodes of the circuit. And in the middle, we have different qubits and we have different gates. And such a circuit have both quantum and classical components. And when we say faults, we really are saying, we really model it using an environment circuit, or just think of it as like an outside environment. And the faults in the circuit interact with both the qubits in the circuit or qubits and gates in the circuit and qubits and gates in the environment. So in the most simple sense, the faults, they happen between the gates, they are inserted before and after each round of gates in our circuit. Okay. And one thing to note here is that even though these faults, they're unitary in the global space, when you look at both the circuit and the environment, these faults are unitary. When you just restrict to the logical workspace, these faults can be non-physical, or I'll explain that on the next slide, but what this is saying is that these faults can really do very annoying things. For instance, they can take a qubit out of the circuit, put it in the environment, swap in some environment state into that place, and after the gate is applied, swap the qubit back. So we do capture very general style of errors and noise, but just hiding away all the details, we think of faults as being inserted before and after the gates. Great. So I promise you to show a little bit of mathematical detail. So what is a fault? We consider an error channel. Error channel, you can decompose it into Krauss operators. And we insert errors between gates. So we have the state. Use a laser. We have the state, we have gates, and between the gates, we introduce different error channels. And if you expand everything, there's a probabilistic distribution over these Krauss operators. Now, these Krauss operators, these are really super operators because they're not just working on the code state itself, they're also interacting with the environment. And these are what we call the faults in the circuit. And if we expand everything, the final circuit looks roughly something like this, where you have a sum over the faults, where with the probability of each fault, and then there's the circuit execution subject to that fault, acting on the state. Okay? So that's what we mean by a faulty circuit. And most of the time, we'll just analyze CF, C subject to this fault, and we think of the faults at this point are being inserted deterministically. Okay? We'll analyze the probability distribution later, but for now, we focus on the circuit C of F.
Can I just ask, why do you use Krauss operators here? Why can't you just purify them to be unitaries?
So they are actually purified into unitaries. That's actually why we have the environment circuit. So,
right. So, sorry, I thought in this formalism, your Krauss operators were acting on the system plus environment.
Yes. Oh, yes. So the Krauss operators, when you look at them as acting on the system and environment, then these error channels become unitary, and these Krauss operators is just a decomposition of the channel. But when you restrict onto just the state X, which is the state that we put into the circuit, to this circuit, they are super operators that interact with this external environment circuit.
Okay, cool. Thank you.
Yeah, thank you for the question. I really appreciate it. Great. But this is where we'll mostly look at. We'll look at a circuit subject to a particular fault. Okay. Great. And how should we model these faults? Because if we just carry all the super operators around, that's really a very difficult way of analyzing a circuit, especially because the super operators they are very limited. We make very limited assumptions about them. So the way that we model these faults and the way that we build this entire formalism is by capturing these faults by sets. Okay? So let's consider like a faulty circuit C sub F. How really does the fault affect the execution? Well, conceptually, the locations of the circuit that this fault corrupts is really critical. Some failure locations can be corrected, some failure locations cannot. And we capture this intuition using the following definition, which is really our most important step of bringing the whole formalism closer to a combinatorial analysis just based on sets, discrete sets. And that's the definition, what we call an avoiding set. So let's consider a bunch of locations or a bunch of qubits. Okay, let's say there are n qubits. A family of sets or bad sets, we call it F, is really just a subset of the power set of n. So it's a bunch of undesirable sets. And let's consider a particular set E. Let's say this is where the error is or where the fault is corrupting the circuit. We say that E is F avoiding if E does not completely contain any subset or any element of F. This is potentially one of the most important definitions. There are a couple of really important definitions in this formalism. This is potentially the most important one. It's really saying that if the set is avoiding on this family of bad sets, that means it doesn't contain any of its element completely. Right, so let me give a few examples to illustrate what I mean. Let's consider just a regular error correcting code. Actually, this doesn't have to be quantum or this doesn't have to be quantum. This can be classical as well. But let's say we define F to be all sets from which a minimum weight decoder cannot recover, or a set of sufficient number of errors that will corrupt the code state to a point that's irrecoverable. Then all the errors E that is F avoiding, they're the ones that are actually recoverable, and we can consider them to be good errors. These are errors that we can use a decoder or use whatever mechanism we have at hand to recover from. So let's look at the example on like a d equals to 2 rotated surface code. Okay, that's what this is. The edges, the qubits are on the edges, these different plackets and these semicircles, they are the stabilizer checks, X and Z. So we can define a particular family of bad set F to be the following. I'm going to play this short video. There's actually a total of 18 sets of weight 2 that you can put on the distance d equals to 2 rotated surface code. These are the errors that if happens on a code, we cannot correct from. But there are 18 of them. And if you look at this particular error, which hits those 2 physical qubits, this is actually F avoiding. And because it is F avoiding, this is actually a correctable error. There is, well, it's actually a stabilizer, I think, but this is actually a correctable error. Great, so this is how we model faults, right? We model them in terms of their support, in terms of the sets of locations they corrupt, and we say that different errors are good or bad, depending on whether they hit enough of the critical locations. Here's another example. So let's consider a circuit, which is encoding an ideal circuit, C, and let's look at all the space-time locations where the faults can occur. So the bad sets in this case, which is really, again, a subset of the power set of N, there'll be witnesses of failed circuit execution. Okay, so here's a circuit. Here's the red parts are all the faults or all the locations where faults has happened. And we have an input state and the output state is going through this faulty circuit. So if the fault is F avoiding with a well-defined F, of course, this depends on the circuit, then we say that the circuit was successful and correct. And what does that mean? So the circuit acting on the state gives the ideal output state, which is the ideal circuit acting on the logical state. Now, it is hard to argue, of course, about the correctness of one big circuit. It is in particular hard if you start with a big circuit and you ask, okay, how do I build this set F? That's actually, one of the biggest questions for this formalism is how to build these sets F. So what we will do is we'll capture this sense of correctness modularly. Instead of arguing about the whole circuit in general, we'll start by looking at very concrete gadgets, and we'll build bigger circuits from smaller gadgets. Great, so that's what I want to talk about next. Fault-tolerant gadgets. So first of all, what's a gadget? For those of us who are not familiar with the terminology, So we say that, what we wish to do is we have a circuit and we wish to implement it with lower error rate and we encode it into a bigger circuit. How is that done? Every qubit of the ideal circuit will be encoded into a code. And similarly, every gate will be encoded into what we call a gadget, which is really just a sub-circuit of CFT, okay? Or where CFT is the encoded circuit. So here's an example. A CNOT gate in the ideal circuit can be encoded into a transversal CNOT, which is what I've shown here, a transversal CNOT between 2 surface code patches. I hope that's familiar, but again, please stop me with any questions. Really actually not sure what's people's background here, but let me know if anything is unclear. So this is a transversal CNOT between surface code. Now, very concretely, right, in C, we have a gate G acting on some sets of qubits. In CFT, we have a corresponding gadget CG acting on error-correcting blocks that encodes the qubits Q. And when there's no error, CG, correctly performs G on encoded qubits, great. And the question that we want to answer is, what if there are errors? How can we say that this, not even the big global circuit, just this small circuit that's implementing one gate, how can we say that that is fault tolerant? Let's start with that. So to talk about it, we'll start by looking at the input and output of a gadget. That's where we'll start. So they are states in quantum codes. They're impacted by errors because even if the gadgets are all doing their job accurately, they can still be impacted by faults and errors. But in general, the input and output state of our qubits of a gadget, these are just quantum states encoded in codes that are impacted by errors. So let's capture that. What do we mean by a code here? It's really specified by 2 pieces of data. One is encoding unitary. That's probably self-explanatory. That specifies the code space. And the second is really what we call a family of bad errors. So this is similar to just the bad sets and the bad faults that we talked about earlier. But essentially, we say that if an error is avoiding on this bad set, then this error can be recovered. This is the 2 pieces of data we ask for a code. And we'll build these specific data for specific codes. We say that this is a code type, but in general, this is all the data we ask for. B can be quite flexible here, depending on how we design the circuit. Now, for a gadget, we'll say, okay, a good input would be one where the error on the state is B avoiding. Otherwise, we call it a bad input. So we are given a bad input is when we're given a state that is already irrecoverable. So there's really not much we can do about it. Right, so let me again return to this example. If we look at the distance equals to 2 rotated surface code, we can define, so this shouldn't be F, this should be B. We can define the bad error supports, and we can look at errors that are avoiding these bad supports. Again, completely combinatorial notion here. So now, after we've talked about fault-tolerant input and output, we can characterize what we mean when a gadget is fault-tolerant. So besides the input errors, faults can corrupt the physical gates in the gadgets, so which will introduce more noise into the system, such as in the transversal C0 case. So on a high level, we say that a gadget is fault-tolerant if, when the noise is bounded, I'll show what bounded means, it's once again using sets. When the noise is bounded, it maps good input to good output. Let me give the more precise definition. For a gadget, such as C sub G, there will be a family of bad faults F. Okay? Again, this is specified for the specific gadget. We'll actually build these fault paths in this paper, and later in this talk, we'll build very simple example. But given a good fault, so when the gadget did not go through too much noise, when the noise hitting the gadget is still correctable, on an input state, which is, the logical state is rho, that's going through a good error, the faulty gadget, the fault is good, the faulty gadget should output the state G sub rho, which is the correct state, the state that you exactly want, because that's the logical action you want to enact, with a good error. So everything is noisy here. Nothing is really, really good, but everything is recoverable. When you give me a recoverable input and I have a gadget that is not failing too bad, I'll give you a recoverable output with the correct logical state. Now, the actual definition looks a lot more complicated than this. I will not show you the whole thing. If you're interested, you can look at the paper, but this is the conceptual idea. Great. We can, just to drive the point, let me illustrate this with a commutative diagram for those of us who likes these kind of things. Here we have an input logical state and an output logical state, and we want to act on it by a gate. And through the encoding map, we really have the input physical state, which is just the encoded state, and the physical output state, and the ideal gadget. Now, what happens is never ideal. The gadget goes through a specific fault, and the input and output each goes through specific errors. And the guarantee here is simply, if the input error is good, and the gadget didn't fail too bad, then the output error is good. This is a completely combinatorial definition here. We're just talking about how how these circuits behaves with different sets, and more importantly, different gadgets with compatible input and output codes can now be very easily composed, right? Because if I have a good input state, I go through a good gadget, I get a good output state, and I can immediately follow it by another gadget that could be a completely different gadget. But as long as the input and output codes are compatible, I can keep carrying this good behavior from the start of the circuit all the way to the end. This is what enables us to compose very complicated gadgets, which I'll show later in the talk. Okay. So now the other question is, we talked about what happens when the input is good. What happens when the input is bad, which kind of will always happen if the circuit is big enough, or if the code, we have, or let's just say we hit like a burst error. What if the input state is bad? Now we make a second definition here. So this is the first one. The second definition says if the input state, oh, sorry, that should say bad error. Okay, I made a horrible, well, I made a correctable error here, but it's not on the screen. This is a bad error. This should say bad error. On an input state with a bad error, when the circuit is still, when the circuit fault is still good, it should output some state with a good error. But this logical state can be arbitrary. In some sense, you're already given an irrecoverable state. There really is not that much else you can do besides just rebooting the whole state and say, okay, let me return to something that I can at least work with. I don't know what that is. All the logical information is lost, but at least my computer is now rebooted again. And we call this second condition friendly. This is a reset mechanism. Not all gadgets has to be friendly. This is an optional property, but I included here just for the sake of ideas. Now, great. So we talked about the inputs being good and bad. What if your gadget's just caught on fire, right? What if the fault is bad? What if everything went wrong in the whole gadget or in the whole circuit? Well, the gadget has failed. There's no guarantee. Let's just say the output state is automatically treated as just bad. But this doesn't mean failure for the global computation. A local gadget failure can be corrected by other successful gadgets, especially when we do like co-concatenation or recursive simulation. So I'll just talk about that very briefly here. Co-concatenation is really a time-tested idea in error correction. The idea is simple. I have a circuit C. Let me first encode it into C1 FT, and I can further encode C1 FT into C2 FT, and I can repeat this for however many times I want. So this is a figure of concatenated encoding from Nielsen and Trong. And the idea here is that if a gadget in C2 FT failed, due to whatever reasons, maybe just your computer caught on fire, that corresponds to just a gate failing in C1. And C1 itself has error correction property, so we can correct that in CF1. That's just co-concatenation. And this recursive simulation method, sometimes they call it level reduction, can be derived under our definitions. I won't discuss it here. It's a very technical theorem, but just want to highlight that this is possible. And this is actually a very common idea or very well-studied idea in error correction. Great. So with that, this is really the definition of a gadget. Good input gives you good output, and bad inputs gives you some rebooted good output. And what we need to be aware here is that these sets can be very hard to construct, right? I told you that in these definitions, I just assume that we have these sets B, we have these sets F, but in general, they can be very complicated for big circuits. And this definition is kind of useless if we can't really properly describe the sets, right? We can talk about sets all day long, but if they cannot be constructed, then we're not being very productive here. So the next part I would talk about is how can we build these bad paths and bound their probabilities, and what happens to these sets when we compose the gadgets or do recursive simulation. This is where I would say everything comes together in this paper. We talked about the models of circuits and faults. We talked about different gadgets and sets. Now is where everything comes together, where the combinatorics meets the probability. And that's actually using this notion called weight enumerators, again, a classical coding concept. But let me define this first. So let's say you just have a family of sets, okay, F, just the same familiar family we had so far. Let me enumerate them a little bit. Let's say I denote this A sub W of F to be the number of elements of weight W in this family F. Okay. I'll give an example later. But the weight enumerator polynomial is really denoted this. So it's W, F is the set as the family of sets, X is a variable, and this polynomial is written out as a sum over all the possible weights, where the leading part is the enumeration, how many elements of weight W I have, and the next term is X to the W. It's a very classic idea from, well, from classical error correction, but this is what a weighted numerator polynomial is. And here's an example. Earlier, I gave you this example where this family has 18 different sets of weight 2, then the weighted numerator polynomial is simply 18x squared. Okay, great. So why is this useful? Why did I define this polynomial for you? Because this polynomial is really the interface between what we say that we separate the combinatorial and the probabilistic analysis. This is the interface. This is where that separation happens. And let me first talk about the probabilistic side of things. So suppose you go through a locally stochastic error distribution E. What does that mean? That means for any specific set, this should be a subset symbol, the probability that that subset is contained in your error set is bounded by epsilon to the weight of S. That's what locally stochastic is. It's one of the most commonly studied noise models in quantum fault tolerance. Then we can show, without too much trouble, it's actually quite intuitive, the probability that E is not F avoiding. This is a double negative here. If it is not F avoiding, that means it's a bad error. So the probability that E is a bad error is upper bounded by precisely the weighted numerator evaluated with the noise strength epsilon. So in other words, the weighted numerator polynomial, it upper bounds the probability of bad errors happening. I showed you the example of locally stochastic distribution, but you can do this for adversarial noise, independent noise, or even coherent noise up to a certain degree. Great, so that's the probabilistic side of things. Now let me talk about the combinatorial side of things. So this weighted numerator makes composing gadgets much easier, or very intuitive. So let's say I have two gadgets with two families of faults, F and G. Let me define two binary operations on these sets. So this is F plus G. This is a new family of sets, which are those that contain a subset from the family F or the family G. And there's F times G, which is the sets that contains a subset from the family F and the family G. So these two are just new families of sets defined on the same elements, except that we impose different conditions on them. These sets are defined, and these notations we picked very suggestively. It is fairly easy to show that if you take the weighted numerator of F plus G, that's just the sum of the two separate weighted numerators, and you take their product, that's just the product of the weighted numerators. And if we translate that back to errors again, this says that the probability that E is either bad for F or bad for G, so this is an or statement, is less than their sum. And the probability that E is both bad on F and bad on G is less than their product. In some sense, this looks a lot like an independent statement, right? This is saying that if you give me two gadgets, then I can analyze the error or the behavior of error on these two gadgets in a very independent fashion, right? So long as the gadgets are independent in a combinatorial sense, they're not overlapping, the above equations hold. And in particular, these two gadgets can be drastically different. They can actually be going through different noise models. The noise can be correlated between gadgets. They can be different, or it can just be, the train running near your optical devices, which I was told was actually a source of error for some of our neutral atom folks. But in principle, the noise distribution can be arbitrary, yet we can analyze these gadgets independently. And this is the key property of our definition, is that we have composable gadgets with no assumptions except that they're mostly disjoint. Great. I just want to mention, we also have an operation defined for concatenation. I'll show you the equation. There's no need to try to read it. The weighted numerator is bounded, as one would expect for concatenated gadgets. There are more details can be found in the paper. I just want to put that in there. So that's about weight enumerators and gadget compositions. Now let me get to the assembly part where we put the combinatorics and the probability together and start proving some gadgets and prove some threshold theorems. So let me start with the simplest gadgets. There's the error correction gadget. Let me start with, again, using surface code as an example. So this is Google surface code with different errors hitting their qubits. We'll define a particular set of bad error supports. You can read this definition, but it may be, kind of just technical for the experts. But we use the notation U subscript C and superscript D. D is the code distance, C is the subscript. All one needs to remember here is that the bigger the value of C is between 0 and 1, the bigger the value, the more errors there are. Okay? So that's a bunch of bad faults that we have defined. And the standard error correction gadget, where we measure the stabilizer for B rounds and correct for errors, that can be written down basically just as usual. So this is a standard error correction gadget, or this is how we draw it out, at least. And there's one thing to note here is that the input is a surface code where the error is parameterized by 1/2. And the output is guaranteed to be the surface code where the error is parameterized by 1/6. What does this mean? Remember that bigger C means more errors. This means that the input error is suppressed by the error correction gadget. And this gadget has a bunch of bad faults. We construct it explicitly and we analyze it. And the weight enumerator polynomial is bounded by something exponential, inverse exponential in the code distance, as long as X is below a constant threshold. So in some sense, this is already a threshold theorem for the basic error correction gadget using the weight enumerators. Now let's start composing. Here's a gadget for C0. I have two logical qubits that first goes through an error correction gadget to suppress its errors, and then goes through a transversal C0 gadget. This is the transversal C0 gadget. And I can build the bad faults of this bigger gadget by composing the bad faults of the smaller gadgets. So the bad faults for this entire gadget is simply the sum of the 3 bad faults of the 3 individual gadgets. There are 2 error correction gadgets and 1 transversal C0. And we can bound the weight enumerator, simply this. It's 2 times the weight enumerator of the error correction plus the weight enumerator of the transversal C0. Right. And since each of the component, you can show that they have a constant threshold, this entire gadget has a constant threshold. We can also do state injection. This is to prepare a noisy logical state into the code. It's an important component in error correction, but let me go through this a little quicker. This is what an injection circuit looks like. We can analyze its weight enumerator polynomial. And once again, we construct everything explicitly. This prepares a logical state in the surface code. And I can use that in magic state distillation, which is a very important procedure for fault tolerance. I can have many injection gadgets followed by a distillation gadget, or I can call this entire gadget a preparation gadget and feed it into a second level distillation where each of these has a first level distillation. All of these can be analyzed using the weight enumerators. All of these can be constructed very explicitly. There are more details in the paper. And if we put everything together, here we have composed like much bigger gadgets out of smaller gadgets. We can compose entire fault tolerant theorems out of it. And that's what this looks like. So this is a threshold theorem for surface code where we bound the overheads of the space and time overhead using surface code of this fault tolerant scheme. This is constructed using transversal Cliffords and magic state distillation. As I mentioned, this is probably, maybe, the first written proof of surface code FTQC threshold. If you disagree with it, please let us know. I will stop calling it the first written proof. This has constant threshold against locally stochastic noise. We also prove a worse threshold against coherent noise, but this is a new result. I don't think anyone has actually written this down before. And the one thing I like to say here is that building the formalism took us about 60 pages, Proving this theorem took us 10, and handling coherent noise took us about 3 pages. To put things in reference, usually a threshold theorem proof takes somewhere between 40 to 100 pages. There has been some coherent noise result on surface code. That particular paper was 100 pages. So what I'm trying to highlight here is that once the formalism is built, proving these theorems actually got much shorter and much easier because now we have set up the library. We prove a constant space overhead. So this overhead on the width is constant using LDPC code. This is a reproduced results from Gottesman's and TKY. This only took us 5 pages, much shorter because we did it later and we already have all of these gadgets from before. And this formalism was also used in this paper that proved this almost log overhead FTQC fault-tolerant computing fault-tolerant scheme. This is from Yuan and Patterson. This is a very complicated result, but it is one of the most asymptotically optimal FT scheme as of now, and it critically makes use of this formalism. Great. So that's the threshold theorems that I want to talk about. Let me just very briefly, I think I can conclude the talk here with some future direction. Let me return to the question we asked earlier. What is fault tolerance? The answer I want to give here is that it's really a combinatorial bound on the fault propagation behavior of a circuit. And by looking at avoiding sets and weight enumerators, the composable FT formalism separates this combinatorial analysis from the probabilistic analysis of noise distribution and make otherwise hard to compose gadgets very easy to analyze independently and at the same time in a composable fashion. Now, we hope these definitions can be groundwork that inspire future proofs of fault tolerance, and there are a lot of future works that can be done here. There's the threshold proofs for LDPC codes. I'm just going to list a couple here that I find interesting. If you're a student working error correction that wants to find some projects to work on that involves proving fault tolerance theorems, come talk to us. So we can try to prove threshold theorems for LDPC code surgery operations. This is a hot topic recently that has seen a lot of improvements and a lot of applications. We can prove thresholds for them. We can derive constant thresholds against coherent noise with specific constructions. This will actually be fairly new results. There's some recent papers doing similar things, but I think overall it will be a fairly new result. And there are these two-dimensional FTQC schemes where the physical dimension is constrained, and we can do it by concatenating LDPC codes. Again, a fairly new constructions that we can do here. So there are many more we can do, and if you are interested in proving this, come talk to us. We always welcome new collaborators. Great, and that's really the end of my talk. Thank you all for being here. I really appreciate the questions. And if you want to find the slides, they're available at this QR code. Thank you.
Okay, yeah, thank you very much for a very informative talk. So I guess we have a bit of time maybe for some quick questions from the audience, some comments. Yeah, Jakob.
Hi, thank you very much for the nice talk. It's not my area, so my questions may be a little bit not very sharp, but anyway, it seems like you don't make much assumptions about the properties of noise, except for that one assumption where you had like the sum of epsilons to the power of the size of the set.
So I should clarify. Oh, sorry, let's stop the screen sharing. Let me share back again. So it's this one, I think.
Yeah, that's right. So I just wanted to ask, how I wanted your comment on how strong an assumption this is and how common it is.
So actually, this is not an assumption. This is what I was saying here is that if you assume your error is locally stochastic, then you can prove this.
Yes, but
can be
I mean the locally stochastic assumption itself.
Great. So the locally stochastic assumption is a pretty common noise model in fault tolerant. It's used in a lot of papers. I here for us, it's an example. If you have other noise models, either adversarial or independent or coherent noise, you can still derive an equation like this, and we derive actually quite a few of them. You can still derive equations like this. You can still upper bound the bad error probability using weighted numerator. It just won't look exactly like this.
I see. And does this hold for like non-Markovian noise as well? Do you guys have something derived for that?
Non-Markovian noise. We don't work with that specifically in the paper, but that's perhaps captured by the coherent noise. So the coherent noise is saying that the global circuit is getting hit by a unitary that is close to the identity in diamond norm. Does that maybe capture non-Markovian noise?
I'm not sure, but I don't think so. I think you need like a unitary across the environment and the system for that.
Yeah. It will be a unitary acting on the environment and the circuit.
Okay.
So maybe it's I think it's my lack of understanding of what would be a non-Markovian noise, but if we see the definitions, I think I would expect there's a way to derive an equation such as this for the particular noise model where we bound upper bound the bad error probability using some equation on the weighting numerator.
I see. And sorry, I have one more follow-up on this. So it seems like your formalism just accounts for where all the bad stuff is. Like, you don't want bad noise on a certain subset of qubits or something like this. But you could in principle have noise touching a certain subset of qubits that's considered bad, but still the noise isn't bad because maybe there's some verifiable property of that noise that you could use to ensure that the code still handles it, even though it can't handle all noise on that subset of qubits. Do you have any kind of thoughts or comments on, extensions of this or, whether your work touches on this?
Right. So it depends on how the noise is modeled. So for instance, when we analyze coherent noise, where the assumption is that you just get hit by a global unitary that acts on the entire workspace and the environment, and all you know is that the global unitary is close to identity in diamond norm. Technically, when you think about it, you would say, well, it seems like it's just hitting the entire set, right? It's just going to hit all the bad sets. There's no way we can analyze this. But in fact, what we do is that, this global unitary can be decomposed into, identity plus like smaller components, these like, epsilon, these are much smaller epsilon probability components. And these smaller components, because the global unitary is close to the identity, these smaller components can be seen as acting locally. So maybe that's partly answering your question. If we understand the noise very well, and even if it may have like large support, if we understand the noise very well, then we can go through this earlier decomposition. Where's that? Go through this earlier decomposition and try to capture the fact that they mostly have their high weight components have extremely low probability that we don't need to worry about them too much.
Okay, well, thank you.
Yeah, thank you for the question. I appreciate it.
All right. Let me see if there's some question from the audience. Okay, don't see anyone. I just have maybe two small questions. So for example, if you, I guess if you know the code, you'd always know kind of what are the bad errors for it, right? Like, is this
You can
kind
always,
of
you can always build a bad set of errors for it. Yes.
Okay, and then like you would always know also, because like the way I imagine it is like kind of like you have all you needed to know to use the framework is kind of like some elementary set of gadgets, because other then you can just compose everything afterwards, right? In some sense.
Yeah.
But I was just wondering, like for any particular code you were interested in, like this is always kind of doable, right? If you have enough information about the code.
Yeah. So
Mm,
actually, for any kind of we mostly work with stabilizer codes in this
mm,
paper, but if you
mm,
just give me a stabilizer code, there are many. We give like very concrete ways of building this bat set, building the error correction gadget, and building a couple of other gadgets that can be useful for the code. So
mhm,
if you want to do some, in some sense, this is like a programming language, right? There are like
mhm,
building functions where you can just call and
mhm,
apply to your specific code. But if you want something kind of more advanced, more specific to your case, you can also try to build, the bad sets yourself.
mhm, mhm. Right. Yeah. I guess like the follow up to that is like, so you showed this table of like how people were doing all of these threshold things. And I guess like on the bottom right, basically that's I would call that like proof by intimidation. Uh,
Yeah,
so
yeah, exactly.
so the thing is like so now one can look at some of these previous results and kind of like, okay, let me try to fix how you were doing the proof and use your framework for this. Like this is something one could do, I guess.
Uh, very much.
Mm,
I think this is like, for instance, I mentioned a couple of future directions here.
mm, mm,
Um, actually, if there are students in the audience interested in
mm,
working on some of this, I want to highlight that these will actually be new results. The framework building part of the work has already been done. That's 60 pages. These shouldn't be too bad, but okay, question mark on that. Anyways, some of these results here, for instance, LDPC surgery, there are other proofs of fault tolerance for these gadgets, but there has never been a threshold proof. And that's really is the gold standard of fault tolerance. So if we can derive a threshold proof for these code surgery techniques, we can immediately compose it with all the other things that has been built in the literature, and then start, um, chunking out a few like FT constructions.
mm. Yeah,
So
yeah,
yeah,
yeah.
and that would correspond to, for instance, in this table, for surgery, what people usually prove is that they have large space-time distance or
Mm,
just large distance. We can quite easily bring these two closer to the rigorously proved side.
mm,